Hello students, welcome back. Let us resume our discussion on hypothesis testing, continued from lesson 11b. In lesson 11b, we went through the introduction to hypothesis testing, namely the mathematical structure of hypotheses, like these, and some exercises on setting up hypotheses, like this, and like that. I hope everybody remembers. And also, we went to an advanced discussion on types of errors as well. This was an optional topic, so many students may have skipped it, and that's going to be okay for the most part. Now let's go to section 2. Hypothesis testing for population means 1, when we know the population standard deviation sigma. By the way, in section 4, we're going to deal with the case that we don't know sigma. What's making the difference? Remember this? We went through this table in lesson 10 and lesson 11a, and after all the steps, at the very last moment, known sigma versus unknown sigma, we use either Z or T tables. Okay, here we go. Here's an example problem. And by the way, we have two solutions. And I'm going to talk about so-called the critical value method in this video and leave the other method in a second video. Again, I'm going to do the same thing here. We'll do only the critical value method in this video and the probability value method in a separate video. Okay, let's come back to this. I hope everybody remembers. It's the very same problem that we went through in section 1. And please remember, we had this setup. Null is 75. So about the same as null of 75 or less than 75 significantly. All right, after the setup, we have some more numbers to work with. Let's see. The mean drying time of 72.3 minutes in 25 observations. So we are talking about sample size of 25 and sample mean of 72.3. Those are straightforward. And the significant level of 0.02. Okay, that too is straightforward. The problem says so. Now, this is an interesting question. Is this a population standard deviation or a sample standard deviation? It came from section 2, so it's population standard deviation, but that's cheating. And if you encounter this problem in an exam with no hint, then you should be able to make right decision. Is it sigma or is it S? Read the problem carefully and place where that standard deviation of 9 minutes came from. It came with a null. So blah, 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 known to be normally distributed with the mean of 75 minutes and the standard deviation of 9 minutes. It came with a null. What do you mean by null? Nothing. Nothing to do with the sample. It came out of nowhere. So it's the population standard deviation, not sample standard deviation. All right? What if I just copy and paste like this? What if I copy and paste like this? Then this is the sample standard deviation, because the standard deviation 9 minutes, that information came along with the sample. 72.3 minutes and 9 minutes in 25 observations. You see, it came from sample, so this is sample standard deviation. So in this case, you'll have to use the t distribution, by the way, small sample size, unknown sigma. But of course, let's go back to the original setting. The original problem was written like this. It came with null value of 75, so it's population standard deviation. So you have tried like this. See the difference? Okay, all right. Now the population standard deviation is known, so we have to use a z-curve. All right, let's draw the z-curve. And I'd like to save some time, so let me just open up and then show you the z-curve. Centered at 75, the null, straightforward. And what is the alternative hypothesis? That's less than 75, right? Less than. And then alpha value of 2%. Combine those two, we have this picture here. Shaded 2% to the left. Make sense? Alternative is less, and mathematically less is to the left. And then how much? By 2%. So what does that mean? There's about 2% of chance that sample mean will fall here in this red region, far away from the null, just by coincidence. And if you think that 2% is low enough so that you will not consider it as coincidence, then, well, that's what this alpha is all about. That's a level of significance. So if anything falls here, then you'll say, hey, that should not be coincidence. It's too low of a chance. So we'll just ditch the null hypothesis and go with alternative hypothesis. It all boils down to finding out this x value, which we call the critical value. So we're looking for this critical value. Once you find out the critical value, then that's going to be pretty simple because once you have this x value, we can now place this sample mean 72.3, assuming that we know this. So if it falls here, then close enough to the null, so the null wins. We will accept the null hypothesis. Now, if it falls here in the red region, then too far away from the null, so I will throw away the null and accept the alternative hypothesis. And that threshold is right here, the critical value. That's the key. Find out the critical value and place this sample mean. We don't use the sample mean until the very last moment when we place it. The key is to look for the critical value. Okay, let's look for the critical value x. How do we do that? Well, here's our old friend, formula number 1. N minus center over SE is the z-score associated to this setting, 2% here. So look up the z-table and the z-score will be about negative 2.05. I'll leave the detail to students because by now everybody must have mastered the use of z-table. And of course the use of formula number 1, N minus center over SE. And then solve for x, you're going to get 71.3, approximately speaking, and that is your critical value. All right, now that you have the critical value of 71.3, placing that sample mean of 72.3, that's easy. It falls in the blue region, close enough to the null, so we will accept the null hypothesis. Does it make sense? If this observed sample mean had been, say, 69.7, then that would fall in the red region. So we'll go with the alternative hypothesis. So we use the sample mean at the very last moment. Decision-making process is pretty straightforward. Close to the null, null wins. Far away from the null, then null loses. That's basically the idea. So you don't have to worry too much about the decision-making process. Let's do it again, this time using a different problem. Again, we went through the very same problem, so I guess it's not going to cause too much trouble to you. So we have this hypothesis, and then all those numbers associated to this problem. Again, sigma of 500. How do you know that? Because the standard deviation of 500 grams came from the null. The birth weight for babies of women living in poverty averages about 2,800 grams with a standard deviation of 500 grams. They came out of nowhere. Nothing to do with sample. This sample of 20 randomly selected babies with the mean birth weight. If this 500 grams came around here, then okay, it's a sample standard deviation, but not in this case. It came here. It's a population standard deviation, so you have to use a z-curve. And pretty much straightforward again. Centered at 2800, the null, and alternative hypothesis is greater, so, and then alpha is 5%, so shade to the right for 5%. Straightforward. Again, we are looking for the critical value of x. Once you find it out, then you can place this 3060 either to the blue region or red region, depending on what this value is. Make sense? Blue region close enough to the null, then null wins. Red region too far away from the null, so alternative wins. So how do you find out this x value? Again, you do the same thing. It's a z-curve, so end minus center over SE. There. End minus center over SE is associated to 1.645. The z-score for 95% here and 5% there. And also the same picture, we went through the same picture, very same picture for 95% upper confidence bound. Either way. Solve it for x, not too bad. You got 2,980 something. Definitely less than 3060. So we come up with this conclusion. 3060 is too big. So there's very little chance, 5% or less, that this comes into the red region by coincidence. So I'll regard that this is not a coincidence. So indeed, there was an increase in birth weight. What if you repeat this problem for a little bit different alpha value, for instance? If I change it into 2%, for instance, and if you do all those, then you're supposed to get about 30-30. The critical value will be about 30-30. You see, you're going to have to do the very same, except that this is going to be different z-score associated to 98%, so it's 2.05. And do your computation about 30-30. Again, 30-60 is too big, so alternative wins, and we go with alternative. It falls into alternative region. You see, the decision-making process is very, very straightforward once you find out the critical value. Of course, if you screw up drawing this picture, then you're doomed. So make sure you draw pictures. Don't just look at the pictures somebody else drew, but please use your own hands to draw. Okay, so much for section 2. We're going to repeat this using the probability value approach. And if you're interested, you can go through that as well. If you want to skip, just go ahead. Just stick to critical value method only. That's fine with me too.